In this video, we'll talk about the derivative as a rate of change. If f is a differentiable function, then the derivative of f at a is defined in terms of a limit. F prime of a, the derivative of f at a, is equal to the limit as h goes to 0 of f at a plus h minus f at a, quantity divided by h. This limit is a limit of a difference quotient, and the difference quotient represents, among other things, the slope of a secant line that passes through the point a comma f at a and a plus h comma f at a plus h. The numerator is the difference of the output values, or the y values, and the denominator is the difference of the input values, or the x values. So we can think of this difference quotient as the slope of a secant line. And as we compute the limit as h goes to 0, those 2 points on the curve get closer and closer together. And we think of f prime of a as being the slope of a tangent line at the point where x is equal to a and y is equal to f at a. The fact that f prime of a, the derivative of f at a, is a limit as h goes to 0 means that if h is very small, then the value of f prime of a is approximately equal to the difference quotient for that value of h, f at a plus h minus f at a divided by h. That's if h is very small. In terms of lines, this means that the slope of the tangent line is approximately equal to the slope of a secant line passing through a point a comma f at a and another point which is nearby. In this picture, you can see this gray line is the tangent line, and this solid blue line is a secant line. And if h is very small, then a and a plus h are close together, and that means that these 2 points on the curve are close together. The closer h is to 0, then the better the approximation. Here we've moved h closer to 0, so we can see that the secant line is closer in slope to the tangent line. So if x is a number that is very close to a, then we can think of x as being a plus h for some small h, and then we have that f prime of a is approximately equal to the difference of the y values divided by the difference of the x values. F at x minus f at a in the numerator, and in the denominator we have x minus a. If you just plug in x equals a plus h, you end up with the usual difference quotient here. Rearranging this, that is, solving for f at x, we get that f at x is at least approximately equal to the slope at a times x minus a plus f at a. We can define this to be a function. We can call this L at x. The function L at x defined in this way, so that L at x is equal to f prime of a times x minus a plus f at a, is called the tangent line approximation for f at a, and the graph of L is the tangent line to the curve at the point a comma f at a. So here we can see the graph of our curve. This is y equals f at x, and this blue line is the tangent line. The equation of the tangent line is y equals f prime of a times x minus a plus f at a. This can be found by looking at the point-slope form of the line and then just adding f at a to both sides. If h is really small, then f at a plus h is equal to L at a plus h. So again, the curve here is y equals f at x, and the line is y equals L at x. That is to say, it's f prime at a times x minus a plus f at a. And we can see that at least when h is very small, the point on the line is very close to the point on the curve. Keep in mind that f at a plus h is the output value. That means it's the y value. L at a plus h is also the y value. So what we're really talking about when we say that these outputs are close, we're talking about the vertical distance between these 2 points. We're talking about the difference in the y values. This vertical distance is our error. It's the difference between the actual y value, which is over here, and the y value that we get using the tangent line approximation, which is here. That difference, that error, is this vertical distance between these 2 points. The basic idea is that if h is really small, then this vertical distance will be very small as well. And so that if we can't compute something using the curve, we might be able to approximate it using the equation of the tangent line, because it's very easy to work with tangent lines. It's very easy to do computations with linear functions. We need to be a little bit careful, though. The larger the value of h, the less accurate the approximation becomes. This is the same picture, but zoomed out a little bit. So h1 was our h in our previous picture. So in our previous picture, we were just looking at this small corner. And when we talk about an accurate approximation, we mean that the vertical distance between these 2 points is small. But as you allow h to get larger and larger, that means you're moving farther and farther away from A. And then you can see that the vertical distance between points is getting larger and larger. And if that vertical distance is getting larger, that means the error is getting larger, so the approximation is becoming less and less accurate as you move further and further away. Tangent line approximations at a point are only good approximations near that point. Let's do an example. Determine the equation of the tangent line to y equals the square root of x at x equals 4 and use it to approximate the square root of 4.1. The basic idea here is that 4.1 is pretty close to 4. And while we might not immediately know the square root of 4.1, we do know the square root of 4. So we want to find the equation of the tangent line. So in order to do that, we need 2 things. We need a point and we need a slope. Well, the point is easy because we know the x value already. X is equal to 4. And y is the square root of x, so it's the square root of 4, which is 2. It's the positive square root. So our point is 4, 2. That's our point. Well, what about the slope? Well, in order to determine the slope, we're going to define a function. We'll call it f at x, and that's going to be the square root of x. Maybe we want to write it as x to the 1/2, so then it's x to the power, so we can easily apply the power rule. Our slope is going to be f prime at 4. So we need to compute this. So in order to do that, of course, we need to use the power rule. So f at x is x to the 1/2, so f prime of x is equal to 1/2 times x to the, we decrease the exponent by 1, so it's 1/2 minus 1. So that means it's 1/2 times x to the negative 1/2, which is often more conveniently written as 1/2 times the square root of x. We want to compute this derivative at x equals 4, so f prime of 4 is equal to 1/2 square roots of 4, which is 1/2 times 2, which is 4. So that tells us that the slope is 1/4. So we have a point, which is 4, 2, and we have a slope, which is 1/4. So that means the equation of the tangent line at 4, 2 is y minus the y value is equal to the slope times x minus the x value. So if we want to find the tangent line approximation, we basically just solve for y. So tangent line approximation is y equals 1/4 of x minus 4 plus 2. And this quantity right here is what we were calling L at x. You could simplify it, but you don't want to. When you're doing these approximations, you want to leave it in this form, because what we're about to do is plug in x equals 4.1, and if you plug in x equals 4.1 into this, then it simplifies immediately. Whereas if you write this out in slope-intercept form, then it becomes a little bit more difficult to do the computations. And the whole reason to do this tangent line approximation is it makes the computations easier. So the approximation for the square root of 4.1, this is equal to f at 4.1, which is approximately equal to L at 4.1, because 4.1 is close to 4. So now we just plug in 1/4 times 4.1 minus 4 plus 2, and this value right here, that's just 0.1. So now we have, let's write this as 0.25 times 0.1 plus 2, and this will be equal to 2.025. And that's our approximation using the tangent line. And the calculator will give that the square root of 4.1 is approximately equal to 2.02485, which is not far at all from what we computed, 2.025, 2.02485. So that's not a bad approximation at all. When x is close to 4, the value of y equals the square root of x is closely approximated by the tangent line there. So this curve that you see here is y equals the square root of x, and this blue line is the tangent line at the point where x is equal to 4. If you're at 4.1, then you're quite close to 4, so you can see that the tangent line is very close to the curve there. And consequently, the tangent line approximation gives you a pretty good approximation of the actual result. What exactly is meant by close in the requirement that h is close to 0 is often determined by the context. Consider the following example. The cost function in dollars of a company that manufactures gizmos is given by c at x is equal to 300 plus 8 times the square root of x plus x cubed over 6, where x is the number of gizmos produced. Compute the tangent line approximation for c at x equals 16. So we want the tangent line approximation, and that's just essentially the equation of the tangent line. So what the tangent line approximation tells us is that for x close to 16, we have that c at x is approximately equal to c prime at 16 times x minus 16 plus c at 16. Again, this is essentially the equation of the tangent line. The equation of the tangent line is y equals this quantity. Okay, so what are all of these quantities? First, we need the derivative. So let's just rewrite c. c at x is 300 plus 8 times x to the 1/2 plus x cubed over 6. I just wanted to write the square root of x as x to the 1/2 again so that I could see that it was x to a power. And now we differentiate term by term. The derivative of 300 is 0, plus 8 times the derivative of x to the 1/2, that's 1/2 x to the negative 1/2, plus the derivative of x cubed is 3x squared, and this is divided by 6. So if we simplify this, c prime of x is equal to 0 plus 8 over 2 is 4, and then it's divided by the square root of x, plus x squared over 2. This is c prime of x. We need to compute these quantities. We need to compute c prime of 16 and c of 16. So we can compute c prime of 16 right now. C prime of 16 is 4 over the square root of 16 plus 16 squared over 2. So the square root of 16 is 4, so this first term is 4 over 4 is 1, plus, and then 16 squared over 2 is 128. So the derivative of c at 16 is 129. Okay, so we needed c prime of 16, and we've just found that. Now the other thing that we need c at 16. Well, that's just plugging in 16 into our original function. So we can compute that directly. C at 16 is equal to 300 plus 8 times the square root of 16 plus 16 cubed over 6. And if you get a calculator out in order to help you compute this, you'll find that this is equal to 1014.67. Well, it's actually 1014.6666 recurring, but if we round it up, since we're talking about dollars, then we round it up to the nearest cent. So it's 1014.67, $1,014.67. So this gives us the y-coordinate corresponding to x equals 16. So now we have that c at x is approximately equal to c prime at 16 is 129 times x minus 16 plus 1014.67, at least approximately. And that's our answer. Now here's a question. What do we mean by close when we say that this approximation is accurate for x close to 16? X is the number of gizmos produced. That means it has to be a positive integer. In this case, it makes sense to think of h being equal to 1. If x has to be an integer, then what would be closer to 16 than 17? Or possibly 15? Generally speaking, if you're looking at a cost function, you want to know how much it will cost to produce one more good. And in this case, we're imagining that we've already produced 16 gizmos. So what we really want to know is, what is the cost to produce one more? And we can use this tangent line approximation to help us answer that question. We know that for x close to 16, we have an approximation given by the formula on the previous slide. So if we just plug in x equals 17 into that formula, we'll have that c at 17 is equal to 129 times the x value minus 16 plus 1014.67. And this gives you 1143.67. You can see on the graph here, this is the graph of the curve, and this is the graph of the tangent line. So these are close together as long as x is really close to 16. 17 is not exactly close, but it's as close as you'll get when you're looking at integers. And if we just imagine drawing a vertical line through here, you can see that at this point, the curve is very close to the tangent line. So we would expect that the tangent line would give us a very good approximation of the actual value. The tangent line approximation at x equals 16 tells us that when x is close to 16, then the cost is 129 times x minus 16 plus 1014.67. Let's just remember that $1,014.67 is the cost for making 16 gizmos. So the slope of this line, 129, indicates that an increase in production by 1 unit will increase the cost by approximately $129. So if you just plug in x equals 17 here, then this quantity, if x is equal to 17, this quantity just becomes 1. So we take the cost to produce 16 gizmos, and to that we add 129. So this 129 tells us the cost in producing one more gizmo. In general, the tangent line approximation at x equals a is given by c at x is approximately equal to c prime at a times x minus a plus c at a. Since the slope of the tangent line when x is equal to a is given by this derivative c prime of a, then we have the following interpretation of the derivative. If we increase the production of gizmos from a to a plus 1, then the cost of production will increase by approximately c prime of a dollars. So that is one interpretation of the derivative. It tells you if you increase by 1 unit, what the increase in cost will be, approximately. In economics, there's a special name for the derivative of the cost function. So if c at x is the cost function representing the cost of manufacturing x units of some product, then c prime of x is called the marginal cost. Similarly, if you have a revenue function, r at x, then r prime of x is called the marginal revenue. The marginal cost represents the approximate cost for producing one more unit after having already produced x units. Similarly, for revenue, it represents the approximate revenue earned for selling one more unit, given that you've already sold x units. We can think of the derivative as a rate of change. If f is a function such that f at x represents some quantity, then we can think of f prime at x as being the approximate increase in f if x is increased by 1 unit. If we can change the units to something smaller, like seconds instead of minutes or milliseconds instead of seconds, then the interval from x to x plus 1 unit becomes smaller, and the approximation of f prime at x to the actual change, which is the difference between f at x plus 1 and f at x, becomes more accurate. So if we're able to consider very small units, then our intervals are very small, and then the derivative more closely approximates changes in the value of the function. It is for this reason that f prime at x is often called the instantaneous rate of change, because if an interval is able to be made arbitrarily small, then the intervals last only what you might call an instant. Let's take a look at an example. If an object is thrown upwards with an initial velocity of 15 meters per second from an initial height of 1 meter above ground level, then the object's height above ground level after t seconds is given, at least approximately, by the position function s at t is equal to minus 4.9 t squared plus 15t plus 1. This 15 is the initial velocity, and this plus 1 is the initial height above ground level. This minus 4.9 is here because it's half of the gravitational constant, 9.8 meters per second squared. We see here a graph of this function. Notice that the stuff below the x-axis doesn't mean anything in terms of the physical problem. We're imagining an object is thrown upwards, and its position above ground level is given by this function. But that's only until it falls to the earth. After that point, it's just on the ground. The graph suggests that it then goes underneath the earth, but that doesn't happen. It actually just stops right here and then is at ground level. So what we're seeing here is not the function over its actual domain, but sort of an idealized domain. But we'll get back to that later. The instantaneous velocity after t seconds is given by the derivative of s. So the velocity v at t is equal to s prime of t, which is equal to minus 9.8 t plus 15. And you can see that if t is equal to 0, then you just end up with 15, which is the initial velocity. When t equals 1, the instantaneous velocity is v at 1 equals s prime at 1 is equal to 5.2. This is a velocity, so it's meters per second. If we go back to our formula, we just plug in t equals 1 into here, and minus 9.8 plus 15 will give us 5.2. According to our interpretation, we would expect that over the next second, our position should increase by approximately 5.2 meters. However, the actual change in position over 1 second from t equals 1 to t equals 2 is s at 2 minus s at 1, which is 0.3 meters. This isn't really accurate because the units are too big, at least relative for this problem. The object that we're throwing straight up is in the air for only a little more than 3 seconds. So when we go from 1 second to 2 seconds, the object has already begun its descent. So that's why the change in relative position is so close to 0, 0.3 meters, whereas we were expecting it to be 5.2 meters. If we increment by 1 millisecond instead of 1 second, then time goes from t equals 1 to t equals 1.001 seconds. And the change in position in this case is s at 1.001 minus s at 1. And this is at least approximately 0.005195 meters. But this is a change over 1 millisecond. So if we travel at this same rate for 1 second, that will give us a change of 5.195 meters. This is very close to the distance traveled over 1 second at the instantaneous velocity of 5.2 meters per second. So we've managed to achieve a better approximation by using smaller units. Alternatively, we could just convert the entire equation so that the domain is measured in milliseconds. In that case, we have basically the same equation, but the constant, the gravitational constant of 9.8 meters per second squared has to be converted to milliseconds. And same with the velocity. The initial velocity was given as 15 meters per second. So if we convert these into milliseconds, then we just end up with some extra powers of 10 in the denominator. So in this case, our function has a domain t in terms of milliseconds. Now notice that the graph is exactly the same. That's because we haven't changed this problem, we're just changing the units. So instead of 1 second, we look at 1,000 milliseconds. So in this case, we can compute the instantaneous velocity at 1 second, but that's v at 1,000 milliseconds, and that's 0.0052 meters per millisecond. And the actual change, we just computed that on the previous slide, is 0.005195 meters. So you can see that the numerical values here are very close to the same. The units are different, but that's because we're looking at velocity over 1 unit time. So the velocity here is 0.0052 meters per millisecond, but we're imagining traveling at that velocity for 1 millisecond. So the distance traveled over 1 millisecond at this velocity would be 0.0052 meters. And that's approximately what we have as the actual change. Let's go back to the original equation where we were measuring things in seconds. What is the domain of this function? That is, how long in seconds is the object in the air before it hits the ground? In order to do this problem, we simply need to find the value of t for which s at t is equal to 0. Because when s at t is equal to 0, that means it's on the ground. So we just need to figure out at what time t we hit the ground. So that's easy enough. minus 4.9t squared plus 15t plus 1 equals 0. This is a quadratic. We can solve this using the quadratic equation. And we have that t is equal to the opposite of 15 plus or minus, and then we're going to have a radical here, and it's going to be 15 squared minus 4 times minus 4.9 times 1. And all of this we divide by 2 times minus 4.9. Now this is the kind of thing that we're going to want to use a computer or a calculator to solve. And what you'll get is you'll get that t is equal to minus 0.0652748, and t is equal to 3.1265. Now these are approximately equals. These are approximations. Now this one right here, the negative one, that doesn't have any meaning for us in this physical context, so we can just rule that one out. The one that we want is t approximately equal to 3.1265. So the object is in the air from t equals 0 to t is approximately equal to 3.1265. And the domain, at least approximately, is the interval from 0 to 3.1265. .1265. And we could guess that from looking at the graph, we could see at least that it was between 3 and 3.5. It looks like just over 3.1. Just over 3.1. And our computations confirm that. Just over 3.1. All right. For our next example, we're still looking at the same position function. And we're asked, what is the maximum height of the object? So how are we going to figure this out? We want to figure out what the maximum height achieved by this position function is. And in order to do that, let's just take a quick look at the picture again, at the graph. Let's go back here. So you can see that this is not the trajectory of the object. The object is going straight up and down. This is giving you position or height above the ground as a function of time. The object goes up with an initial velocity of 15 meters per second. As it's going up, it's being acted upon by gravity, which is causing it to decelerate. So the object is going up, but at a decreasing velocity. Eventually, at the peak, the velocity is 0, and then the object will begin falling downwards. And now the speed of the object will increase, but the velocity will continue decreasing. That is to say, we will now have a negative velocity. The velocity will increase in size or magnitude. That's the speed. But there's a negative sign in front of it. So we're becoming more and more negative, so to speak. So as it goes down, as the object goes down, the velocity will become more and more negative. So we start with a velocity which is positive, and then as we reach its peak, we become 0, and then the velocity becomes negative as the object falls to the ground. So what we can infer from this discussion is that at the peak, where the object is at its highest point, the velocity is 0. So in other words, if we want to determine the time at which we are at the highest point, we need to figure out the time when our velocity is 0. And that's exactly what we're going to do. We're going to find the time, find the value of t for which the velocity is equal to 0. So for this time, for that time, s at t will be at its maximum value. Okay, so the thing that we need to do is we need to figure out what the formula is for the velocity. Well, the velocity is just the derivative of s, the derivative of the position function. So it's the derivative with respect to t of minus 4.9 t squared plus 15t plus 1. And we just differentiate it term by term. So we'll have minus 4.9 times 2t to the 1 plus 15 times 1 plus 0. So our velocity at time t will be minus 9.8 t plus 15. Once again, our height will be at the maximum value, precisely when the velocity is 0. So we need to determine when this is equal to 0. So minus 9.8t is equal to negative 15. Divide by negative 9.8, and you have t is equal to 15 over 9.8, which is 1.53061. So at this value, our velocity is 0, and that's when our height will be at its maximum. So if we want to compute the actual value of the height, we want to compute s at this value of t, which is 1.53061. So we just take this value and we just plug it in for t. So wherever there's a t, we just replace it with this number. So it'll be minus 4.9 times t squared, 1.53061 squared, plus 15 times 1.53061, and then finally we add a 1 to it. Now again, this is the kind of thing you want to use a calculator or a computer to compute, and this will be approximately equal to 12.4796 meters. So the maximum height achieved is approximately 12.4796 meters above the ground. Let's look at another example. We can talk about the rate of change of various quantities, not just position or speed. We can talk about, for example, temperature. If a cup of tea having temperature 95 degrees Celsius is left in a room having an ambient temperature of 20 degrees Celsius, so this word shouldn't be there, the idea is that would be room temperature, then the temperature after t minutes is given by this formula. T at t is equal to 20 plus 75 times e to the negative t over 25. So the capital T is the temperature and the lowercase t is the time. So the temperature after t minutes is equal to 20 plus 75 times e to the negative t over 25. This formula follows from Newton's law of cooling. So the question that we're asked is that after how many minutes is the tea cooling at a rate of 1 degree Celsius per minute? Basically, that's asking for what value of time, for what value of little t is the derivative of capital T equal to minus 1. Now notice that there's a minus here. It says that the T is cooling at a rate of 1 degree Celsius. Since it's cooling, there's a minus sign there. And it's 1 degree Celsius. So we're looking for the value of T for which the derivative of capital T, evaluated at lowercase t, is equal to negative 1. Well, in order to compute that, we need capital T prime at t. This is going to be equal to the derivative with respect to lowercase t of 20 plus 75 times e to the minus t over 25. This is going to be the derivative with respect to t of 20 plus the derivative with respect to t of 75 times e to the minus t over 25, just differentiating term by term. Of course, the derivative of a constant is 0. So we end up with 0 plus the derivative with respect to t of 75 is a constant. So we can take that constant out and put it in front. So we just take this constant out here. So this will be 75 times the derivative with respect to t of e to the minus 1 over 25 times t. Now I've written it like this so we can see that we're using the exponential rule. The derivative with respect to t of e to the k times t, where k is a constant, is equal to k times e to the kt. So in this particular case, we're going to let k equal negative 125. Therefore, t prime at t is equal to 75 times the derivative of e to the kt. So that's just going to be k, which is minus 1 over 25, times e to the k times t, minus 1 over 25 t. So 75 divided by 25 is equal to 3. So this will be a negative 3 e to the minus t over, that's supposed to be a t over 25. Now what we want is we want this to be equal to negative 1. So now we just solve for t. So the first thing to do is to divide by negative 3. So we're just going to divide by negative 3 here and negative 3 here. So that means we'll have e to the negative t over 25 is equal to positive 1/3. Now we apply the natural logarithm to both sides, and we'll have negative t over 25 is equal to the natural logarithm of 1 over 3. And so solving for t, we get that t is equal to negative 25 times the natural logarithm of 1/3. Now, if you want to find out what this value is as a decimal, you're going to need to use a computer or a calculator or something like that. And what you can find is that this is, at least approximately, this is equal to 27.4653. What that means is that just under 27.5 minutes, the tea will be cooling at a rate of 1 degree Celsius per minute. So a very natural question would then be, what is the current temperature of the tea? And that's our next question. What is the temperature of the tea at the time that it is cooling at a rate of 1 degree Celsius per minute? Well, actually, we just have to plug in the value of t that we computed. So we know that t at time t, so capital T at lowercase t, is equal to this formula. It's 20 plus 75 times e to the negative t over 25. So let's just write that down here. So it's 20 plus 75 times e to the negative t over 25. And we know this is happening. This happens when t is equal to, and I'm not going to use the approximate value, I'm going to use the actual value, the exact value. So it's minus 25 ln 1 over 3. Okay, so all we have to do is take this value of t right here, and just plug it in right there. So t at negative 25 ln 1/3 is equal to 20 plus 75 times e to the negative, and then we just plug in our value for t here over 25. But our value for t is minus 25 times ln of 1/3. Okay, well, this minus sign cancels with that minus sign, and This 25 cancels with that 25, and what are we left with? We're left with 20 plus 75 times e to the ln of 1/3. Well, e to the ln of 1/3 is 1/3 using the cancellation laws. So this is equal to 20 plus 75 times 1/3. But 75 times 1/3, that's a third of 75, is 25. And so that gives us 20 plus 25 is 45. So the temperature of the tea at the time that it's cooling at a rate of 1 degree Celsius per minute is 45 degrees Celsius.